Okay, so hello and welcome back. So in this video we want to do exercise number 11, which seems to be a little bit complicated, but it's really not. And I'll show you what I mean by that. So I did happen to solve this exercise before. I will just simply erase all of the things that I've written here so that we can move forward. Okay, so the question that we have is basically exercise number 11, which is show that the relation R in the set A. So you have some relation R, you have some set A. The set A is all the points in a plane. So the set A is basically all the points in a plane. So that you can imagine that basically set A basically contains all the points in a plane. For example, x comma y, and any point that you might find over here that belongs to the set A, right? So basically, if that is the case, then A is the set of all the points in a plane, is the set of all the points in a plane, and R is basically a relation on this set, which is all the ordered pairs P comma Q, basically such that distance of the point P from the origin is the same as the distance of the point Q from the origin, right? So the distance of the point P from the origin is the same as the distance of the point Q from the origin. Now I want to show that basically R is an equivalence relation. Now to show that basically R is an equivalence relation, basically you need to show that first of all R is reflexive, and then R is symmetric, and then R is transitive, right? So in order to do that, first let's start with reflexive. So let's start with reflexive. So if R has to be reflexive, then A comma A has to belong to R for every A belonging to A, right? Which means that, and that is already the case because if I imagine that A is some point in the plane which has some distance from the origin, then again A is the same point having the same distance from the origin. Therefore you can say that basically the point A comma A belongs to R for all A belonging to A, right? And so then you can say that based on this, you can say that R is reflexive. R is reflexive. Second, what you can say is that basically about R being symmetric, is that you need to show that basically A comma B belonging to R implies that B comma A belongs to R for all A and B belonging to A, right? So which means that basically if you suppose that for example some some a comma b does belong to R, what that means is that the distance of the point A from the origin is the same as the distance of the point B from the origin, which also means that the distance of the point B from the origin is the same as the distance of the point A from the origin, which implies that B comma A also belongs to R, right? And so what that means is that since A comma B belongs to R implies that B comma A belongs to R, you can say that basically R is symmetric. R is symmetric. Now about R being transitive, what you need to basically, the condition that we have is that, let's suppose that, for example, say if A comma B and B comma C belongs to R, if that implies that basically A comma C also belongs to R for all A, B and C belonging to A, that means that R is transitive. Now let's suppose that some A comma B and B comma C, let's suppose that some A comma B and B comma C belongs to R, meaning that what that means is that the distance of the point A from the origin is the same as the distance of the point B from the origin, and then this means that basically the distance of the point B from the origin is the same as the distance of the point C from the origin, which means that basically the distance of the point A from the origin is the same as the distance of the point C from the origin and that implies that basically if the distance of 2 points from the origin are the same, they belong to R. So I can say that A comma C also belongs to R. So over here we are saying that A comma B and B comma C belong to R, and A comma C also belongs to R, which means that basically R is transitive. R is transitive. So what that means is that R is symmetric, R is reflexive, R is transitive, therefore R is an equivalence relation, right? Which means that R is an equivalence relation. Now the second part of this exercise is basically you want to show that basically the set of all points related to a point P not equal to 0, 0, meaning that P is not the origin, is the circle passing through P with the center, with the origin as the center. Or you can say that with the center of the circle as the origin. You can say that way as well. Now, basically the set of all points related to P, now suppose that P even if P is basically the origin, that doesn't really matter. It does really matter, of course. You cannot say that, but suppose that P is not the origin, is some point in the plane, right? Now, under R, which is basically all of these ordered pairs P comma Q, and the distance of P from the origin is the same as the distance of Q from the origin, and if that's the case, then P comma Q then belongs to R, right? That's the condition that we have here. So then the set of all points related to P, and assuming that P is not the origin, is the set of all points that have the same distance from the origin as the distance that P has from the origin. Meaning that, for example, P has some fixed distance from the origin. Meaning that P has, let's say that P is some point over here, and it has some fixed distance from the origin. Let's call that distance D, right? Now the set of all points being related to P is basically all the points in the plane that have the same distance as P from the origin. Meaning that you would come up with all of these points over here. And so on and so forth. Right? So as you can see, you will come up with a circle that goes through P, and has the center as the origin, or you can say that basically it has with the origin as the center. That's basically the same thing, really. So that's basically what it means. Now, I suppose we have already the logic that I use in all of these sentences is basically was logical enough, but let's see, let me find a better way of expressing the same thing. So here in the solution, we have the set of all points related to P not equal to 0, 0 will be those points whose distance from the origin is the same as the distance of the point P from the origin, which is what I said, right? In other words, if O with 0, 0 is the origin and OP is equal to K, then the set of all points related to P is at the distance of K from the origin, right? Hence, this set of points forms a circle with the center as the origin, and this circle passes through the point P. That's basically what I said. So that means that basically this part over here is shown now, and then that would be basically too many sentences for me to write here. You have already access to all of these solutions, of course. If you happen to need them, you can go over here, and you can go to the tivaracademy.com. You can go to the tivaracademy.com, and over here, if you scroll down, you will see that you will have this is supposed to be, they have changed their home page a little bit. Now, you can go to NCERT solutions, and you can go to class 12, and you can go to, for example, here you can choose class 12 mathematics, and then you can go to chapter 1 relations and functions, and then over here you can see study online exercise 1.1, study exercise 1.1 solutions in English. This is in Hindi, and this is download exercise 1.1 in PDF. And once you download that, you will get another tab in your browser. Depending on how your computer works, you might get a file, and then you might open that file in using, for example, Adobe an Acrobat Reader or something like that. Some software that opens the PDF files for you on your computer, and then you will get some file like this, and then you will have access to all of these solutions, right? So now let's see what we have with example number 12. So example number 12 is basically we have, well, let me actually make a new layer here because you don't really know how much space you need. Okay, so it's number 12 is that show that the relation R that is number 12. Show that the relation R defined in the set A of all triangles, defined in the set of all triangles as R is equal to T1 comma T2. These must be two triangles such that T1 is similar to T2, such that T1 is, and similar, basically when you want to say that two triangles are congruent, you use the, this is congruent. Now I have forgotten that the notation there, so let's, so anyway, T1 is similar to T2. Similar to T2. And hopefully you already know the similarity of triangles. There is basically two concepts in triangles in which you can compare triangles. There is basically triangles could be congruent and could be similar. Similar is a little bit different from congruent, meaning that, for example, if you have this triangle over here, suppose that you have this triangle over here, and again you have this triangle over here, supposing that basically these two lengths are the same, these two lengths are the same, these two lengths are the same, and therefore these two angles are the same, these two angles are the same, and these two angles are the same. So then you can say that the triangle ABC and triangle basically DEF, so you can say the triangle ABC is congruent to the triangle DEF, right? That is two congruent triangles, and there are some basically criteria that you can use in order to specify whether two triangles are congruent or not. For example, there is the criteria of SSS, meaning the three sides. If the three sides of two triangles are equal in size, then the two triangles are congruent, meaning that if the three sides are of the exact same length, then the three angles will also be equal angles, and so the two triangles will be congruent. There is, for example, SAS. There is, for example, ASA. There is, I think there is 4 of them. There is also RHS. These 4 conditions are there. So you can compare the three sides of the triangles, and this SAS means that basically side angle side, meaning that if this side is equal to this side is equal to this side, and the two angles are equal, then the two triangles are congruent. If if you have angle side angle, meaning that if you have this angle over here equal to this angle equal to this angle, and this side equal to this side, then the two triangles are going to be equal, meaning that automatically this side will be equal to this side will be equal to this side, and this angle will be equal to this angle, and that is ASA, angle side angle. And you can see that this side has to be between the two angles, right? So this side is between the two angles. There is also the RHS, which means that if basically you have two triangles over here, if you have two triangles over here, and this RHS is related to right triangles, only to right triangles, not the triangle has to be a right triangle so that you can use RHS. Now, if you have a right, basically in two right triangles, of course, you always have two right angles. I'm sorry, you always have one right angle in each of those triangles. So this is a 90-degree angle, this is a 90-degree angle. Now, if the length of the hypotenuse of this triangle is equal to the length of the hypotenuse of the other triangle, and the length of two other sides of the triangle are equal, so suppose that, for example, this length is equal to this length, then you can say that basically the two triangles are congruent, meaning that, for example, you can say that the hypotenuse is equal to the hypotenuse, and these two lengths are equal, so the two triangles will be congruent. And you can say that suppose that for example this length is equal to this length, which means that the hypotenuse is equal to the hypotenuse, and then this length is equal to this length, and you just simply forget about this length here. If that is also the case, then you can say that the two triangles are also congruent. It just has to be basically the hypotenuse along with basically one of the other sides. So it could be this side or it could be this side, but then you have to find the corresponding side in the other triangle and then show that that side is equal to this side in the triangle that you're talking about. And then you can conclude that the two triangles are congruent. And of course you can see that when two triangles are congruent, the angles are the same in both exactly the same in both the triangles, and the triangles are the exact same size, meaning that this triangle ABC is the exact same replica of the triangle DEF. Meaning that size-wise and angle-wise and everything-wise, they are completely identical, okay? That means congruence, right? Now, suppose that I have this triangle over here. Suppose that I have this triangle over here, something like this, and then I multiply the side length of each of these sides by, for example, 1.5. So for example, I draw this as this way, and I draw it this way, and I draw this way. Of course, this is a little bit different, but suppose that let's assume that this is ABC and this is DEF, for example, right? Let's suppose that AB is equal to, for example, one half DE. Let's suppose that AC is equal to 1/2 DE. 1/2 DE, this is supposed to be F. This is supposed to be F. So AB is equal to, let's say that AB is equal to 1/2 DE. And let's say that AC is equal to 1/2 DF. And let's suppose that CB is equal to 1/2 basically EF. or FE, right? So that means that I have taken this triangle and all the side lengths I have multiplied by 2, and then I've gotten this triangle over here. So since the sides are basically proportional in size, since these sides are proportional in size, the corresponding sides between the two triangles are proportional in size, meaning that EF is 2 times BA in size, DF is 2 times AC in size, and EF is 2 times BC in size, right? So then if you actually try this, you will see that the angle measures will remain exactly the same. The angle measures will not change. Meaning that you can say that basically this angle is equal to this angle is equal to this angle, and this angle is equal to this angle. The angle measures will not change. Okay, so I was unfortunately or fortunately this interrupted by my neighbor, but I think I was talking about the similarity of these two triangles. So again, you can see that basically these sides stay proportional to one another because every side length is being multiplied by the same factor, meaning that AB basically times, for example, AB times 2 is equal to ED, or AC times 2 is equal to DF, or BC times 2 is equal to EF, right? Which means that you can say that, for example, AB to DE is the same thing as BC to EF, which is the same thing as, for example, AC to DE. But of course, since you know that these are ratios, you're not supposed to mix them up, meaning that you cannot write, for example, AB to DE is the same thing as, for example, instead of writing BC to EF, you cannot write EF to BC. That doesn't work because this ratio is not the same as this ratio, right? So the ratios basically remain the same, and what that means is that the triangles are similar, but they could be the size could be different, meaning that of course you can say that these two triangles are congruent, and you could say that they are also similar, meaning that the scale factor here, for example, is equal to 1, meaning that this side has been multiplied by 1 and you've gotten the same triangle, the exact same side lengths. But then over here you can argue that, for example, the scale factor has been 2, for example, or it has been 1/2, or however you want to consider that in that particular case. Now there is this notation here that I have forgotten actually, which I wish to remember. Okay, so the scale, basically the notation that you use here is that you say that basically if two triangles are supposed to be congruent, you write them as the triangle ABC. ABC is congruent to triangle DEF, to triangle DEF. That is basically, that means is congruent to. And these two triangles, as you know, they are similar, so you can say that these two triangles are similar. So you can say that the triangle ABC is similar to the triangle DEF. And as you can see, the vertices are important, the order of the vertices are important, meaning that I cannot say that, for example, the triangle, for example, BAC is similar to the triangle, for example, DEF, triangle DEF, that just doesn't work, because now I'm assuming that basically this vertex B fits basically corresponds to the vertex D in this triangle, which is not the case. You can see that over here you have some acute angle, over here you have a 90-degree angle, so this is not right. You have to basically, in both of these cases, in the case of similarity, and this means that is similar to, and in both of these cases the order of the vertices is important. So that was a little bit about congruence and similarity of triangles, and just to make sure that we have touched upon almost everything necessary here. So basically there are these 4 rules over here. These are the rules of congruence of triangles. There is some rules, some similar rules in the case of the similarity of triangles as well. And they are, I don't know, SSS, and there is a couple of them here. I don't really remember them right now, but I suppose that's not really important right now. So let's see how we can now solve the problem. We can now solve problem number 12, right? So problem number 12 is saying that, and I'm going to just simply make a screenshot here, and I'm just going to make it, that's actually not really required. Okay. So what I'm going to do now is that basically what I'm going to do now is that, so let's see, the question was that show that the relation R defined in the set of all triangles as R is equal to all the order pairs T1, T2 such that T1 is similar to T2. So we have this relation on the set of basically all triangles. Well, I suppose by all triangles, what is meant is all triangles in a plane, I suppose. Meaning that all coplanar triangles, right? You want to show that this relation is an equivalence relation. Is an equivalence relation. And moreover, there is another part to this question that we will discuss later, once we have shown that this relation is an equivalence relation. So first of all, you want to show that, since you want to show that it's an equivalence relation, you need to show that basically R is reflexive. You need to show that R is reflexive. Now, to show that R is reflexive, what you need to do is that basically we said that A comma A belongs to R for all A belonging to A. If that is the case, then we can say that R is reflexive. And of course, since every triangle is similar to itself, since every triangle is similar to itself, therefore A comma A belongs to R for all A belonging to A, and so you can say that basically R is reflexive, right? So that is that. Now the next part is, okay, so then basically now we have established that basically R is reflexive. So now to show that basically R is symmetric, to show that R is symmetric, okay, so to show that R is symmetric, so that basically the condition for R being symmetric is that if basically A1 comma A2 belonging to the set R implies that A2 comma A1 also belongs to the set R for every A1 A2 belonging to the set A, right? So that is the condition. Now you can argue that suppose that for example A1 comma A2 does belong to R. That implies that basically A1 is a triangle which is basically similar to the other triangle. That implies that A1 is a triangle similar to A2, which means that A2 is also a triangle, right? So since A1 is similar to A2, so of course if you have two triangles, basically if you have, for example, triangle ABC, let's say you have triangle ABC and triangle DEF, and if triangle ABC is similar to the triangle DEF, then of course by definition that implies that the triangle DEF is also similar to the triangle ABC, right? So based on this, you can say that this implies that basically A2 is also a triangle, similar to A1, which means that basically you can say that A2 comma A1 does belong to R as well. So over here we are assuming that A1 comma A2 belongs to R, and then we have established that A2 comma A1 belongs to R as well, which means that basically R is symmetric. Right? Now to show that R is transitive, let's suppose that, for example, let's assume that some T1 comma T2 belongs to R, and also let's assume that some T2 comma T3 also belongs to R, right? So this implies that basically T1 is a triangle similar to T2, and also T2 is a triangle similar to T3. So since this T1 is similar to T2 and T3 is also similar to T2, then you can say that T1, T3 are also similar triangles. That means that T1 and T3 are similar triangles. Which implies that T1 comma T3 also belongs to R. which means that R is transitive. And I'm saying that based on the fact that basically the condition for transitivity of R is that if A1, A2 and A2, A3 both belong to R, that implies that basically A1, A3 also belongs to R for all A1, A2 and A3 belonging to A. That is the condition for transitivity. And based on this and based on this definition and based on this argument, you can say that R is transitive, right? So now we have established that R is reflexive, symmetric and transitive, which means that R is an equivalence relation, right? So that was the first part of this question, which we wanted to show that basically R is an equivalence relation. The second part of this question is that we want to show that consider three right angle triangles. Consider three right triangles. Three right triangles. T1 with sides 3, 4, 5. T1 with sides 3, 4 and 5. T2 with sides 5, 12 and 13. 5, 12 and 13. And T3 with sides 6, 8 and 10. So you have these three triangles, and which triangles among T1, T2 and T3 are related? Which triangles among T1, T2 and T3 are related? So basically over here we are saying that basically the relation that we have here is T1, T2, such that T1 is similar to T2. So that means that if T1 and T2 are similar triangles, they will be related under this relation. Which means that all you need to do is to make sure, or to decide whether T1 is similar to T2 or is similar to T3, or T2 is similar to T3, and that whichever one is the case, then those two, that pair of triangles are related under R. So we have basically T1 and T2, which we can basically to decide whether they are basically similar or not. Or you have T1 and T3, and then you have also T2 and T3. So about the first case, basically you have triangles T1 and T2. So if the ratio of the sides are the same, then you can say that basically the triangles are similar. And now here I'm just simply assuming that these sides have been given in the same order, meaning that these side lengths basically denote the corresponding sides in all of these triangles, meaning that, for example, suppose that I have these three triangles over here, I have these three triangles over here, right? So, and suppose that this is for example T1, and this is T2, and this is T3. And if I call this, for example, if I call this triangle ABC, and if I call this triangle, for example, DEF, and if I call this triangle G, for example, HI, if the three triangles are similar, then I can write basically in this exact order that I'm about to write this expression. I can write basically the triangle ABC, for example, is similar to triangle DEF, is similar to the triangle GHI. The triangle GHI, right? Which means that basically the way that I have written these triangles, the way that I have written this similarity relationship between the three triangles, if I consider basically, for example, these two triangles, what I will find out is that basically the corresponding sides of these two triangles would be these two ones, and then the corresponding these two sides would be also corresponding sides, and these two sides would be also corresponding sides, because I have written them in this order. And of course, then assuming that they are similar, then the side lengths are in the exact same ratio, right? And what that means is that I cannot take, I can take in between these two triangles, I can write AC to DF. I can write AC to DF. Actually, this is supposed to be F. I can write AC to DF is the same ratio as AB to DE. AB to DE is the same ratio as, for example, CB to FE. CB to FE. And of course, well, if the two triangles are similar, then these three are going to be the exact same ratios. But you cannot change the order of the sides, meaning that, for example, these two sides that I have put over here, these are corresponding sides. These two sides that I have put over here are corresponding sides, and these two sides are again corresponding sides. Which means that, and now I'm assuming that basically the side lengths that have been given here are again in the exact same order, are corresponding sides of these triangles T1, T2, and T3. So now let's decide whether these triangles are which pair of these triangles are actually similar triangles. So for example, in the case of T1 and T2, you can say that if T1 and T2 if basically T1 and T2 are similar, then this relationship has to exist between the sides, meaning that then 3 to 5 is equal to 4 to 12 is equal to 5 to 13 has to be true. Must be true. If this ratio is true, then you can say that T1 and T2 are similar. Now you can see that this is 3/5, this is 4/12, which is the same thing as 1/3. And of course, you know that 1/3 and 3/5 are not the same ratio, so you don't even need to check the third part here. So this is not the case. Moreover, if I check T1 and T3 here, and I'm really hoping that they have not given us these side lengths in a mixed up order. I really hope so. So if I take, now I can say that if basically T1 is similar to T3, T1 is similar to T3, then the ratio basically 3 to 6 is equal to 4 to 8 is equal to 5 to 10 has to be true. So 3 to 6 is the same thing as 1 to 2. 4 to 8 is the same thing as 1 to 2. 5 to 10 is the same thing as 1 to 2. That is, this ratio is true, which means that basically T1 is actually similar to T3. And also by the same logic, you can say that if T2 and T3 are similar, then these ratios have to be the same, which is not true, meaning that 5 to 6 is not the same thing as 12 to 8. So T2 and T3 are not similar. This is not similar either. These two are similar. So then you can say that T1 and T3 are related because they are similar triangles. They are related under this relation R. Let me check my answer over here. T1 and T3, then the triangle T1 and is similar to T3, hence T1 and T3 are related. Okay. So that was question number 12. Now in the next video we will talk about question number 13. I'll see you in the next video.